So yeah, these are the links that would be useful, like the resources to get to the FBMN stats guide. You can access it through the web app, which is now hosted by the GNPS2 software, which I showed earlier. And then you could also download it from the functional metabolomics web page from the resources, like, yeah, resources stats guide. I would just show you quickly. So you have to just go to the functional metabolomics page, resources, where you could find all the available softwares, and you could just click on the download to download the Windows format .exe files. I hope you would have done that yesterday. If not, you could still do it in the meantime, so we could play around a little bit with that. So yeah, this is the downloaded link. And as I mentioned earlier, this is how you could get from the GNPS2 task page. And I also want to mention one thing that, like, you might wonder, there are tools like MetaboAnalyst, why do another FBMN stats guide? But I want to mention that the idea was to basically bring these R packages and R scripts and Python scripts, because people are more used to scripting languages, and you have all these immense of information about GNPS, MZMind, and about statistics, which is kind of scattered together. And as I mentioned earlier, this is also an attempt to bring all that into like one platform, like a protocols paper. And that's what we did with the Hitchhiker's Guide to Statistical Analysis of FBMN networks from non-targeted metabolomics data. And yeah, to say a few things about this project, we actually started with this like 2 years ago. That was my first workshop. I see some faces from the workshop. They would have also seen that started it with Jupyter notebooks, with our Jupyter notebooks especially. They're playing around with it. But then we also built a community from there, from these workshops, which is our virtual multi-omics lab. And so many of the participants also become part of the lab, and they contributed hugely project as well as testers, and some were also helping with the codes and stuff. So yeah, a huge shout out to them. So we have our Python scripts of all the pipeline that I'm going to show. And in addition to that, we also have it in Chime too, which is a popular platform in the microbiome field. And we have these scripts in the form of Jupyter Notebook format, which is an interactive notebook format. Some of you might know that. And, we also provide along with the protocol, the guidelines to how you could install these notebooks. Start with it. I would get to that quickly. Since we already have these scripts, Axel came up with this idea that why not just put it into a nice app, lower the entry barrier further for like beginners. That's how we came up with the FBMN stats guide. So with the other options available along with this FBMN stats guide, I wanted to walk you through a little bit about like the other platforms that the other scripts that we have. So first is to read, of course, the protocols paper that we have. And if you have scripting like knowledge, or if you want to learn it, you can just choose between R, Python, or Chime 2, as you can see in the decision tree. Like if you have like a large number of samples, let's say more than 100 samples or like more than 1,000 features, these are kind of like not actual numbers, but just to give an idea. You could go with the local installation of Jupyter Notebook, which runs in your local computer, and you could run these with Chime 2, Python, or R. Whereas if you do not want to run for so many number of samples, but only with little number of features, you could also run these Jupyter notebooks in Google Colab platform, which is just another like wonderful resource provided with Google, the same as the Google Doc, where you could just basically run these codes in Google Colab format. But then if you don't want to do any of this, you could simply go to the FBMN stats guide web app. My personal favorite is still the scripting languages. You can play with it, and also, yeah, you could add more modules in it. But then FBMN stats guide already does a very good job in introducing you to the basic statistics. And here I have some screenshots of how the Jupyter Notebook looks within a Jupyter Lab interface. Before going into that, how many of you are familiar with Jupyter Notebook? Can I ask? Cool. Just to introduce a little bit about Jupyter Notebook, because I'm talking a lot about it. Basically, it has these code cells and markdown cells, which is easier for somebody to share, the same as the Google Doc, where you have this information in these markdown cells, they call it, or text cells, and you also have these code cells, which just perform like few lines of codes, and you could see the outputs like right after the code cells, which is easier to interpret. And also for these projects, it's easier also to share and see all the steps that they've done and what sort of results that they've got with each of these steps. That is what basically Jupyter Notebook does, and it basically comes in Python format, but you could all Python kernel, but you could also run it in other kernels like R. And you need to install it. The installation guidelines I've provided in the protocol. I don't want to go deep into that now, but you could also run it through Google Colab, which does not require any installation. The same as the Google Doc, and get into the notebook and start running the script. So enough on the Jupyter Notebook and more on FBMN Stats Guide. This is how you could, this is where you could find the FBMN Stats Guide link, and you could just click on the download as I mentioned. And this is what we are trying to provide with the Stats Guide app. And to say a little bit about what are the things that we obtained from the previous days. With MZMind, we obtained this feature table or feature quantification table. And then we have the metadata table. We didn't talk much about that. I will talk about this, which is a user-generated metadata table. And then you also get different annotation tables from GNPS and also from CPS. So the feature table, you could see that each, as also George mentioned earlier in the talks, that each row contains the samples, different sorts of samples, which could be samples and blanks, controls, all those things, and each column represents a feature, and with the feature intensity in each of these cells. This could be also vice versa, and some tools might have the features in rows and the samples of the columns. But then once you have this feature table, for example, as an MZMind output, in order to also run your feature-based molecular networking, you might not need metadata table as a necessary thing to run feature-based molecular networking. You could still run it, but it would be nice to create a metadata table and then run it on feature-based molecular networking, because that is essential. This is the groups that you saw in the Cytoscapes session, as well as in the GNPS session, when you clicked into this, all these little things like attribute sample type for all these pie chart representation. So in order to create this metadata table, you first need to copy all these file names, and you have to put it in the first column, and it has to be file name. This is also something we learned. It should not be file names, but file name, because GNPS has full vocabulary. And also, in addition to file names, you have additional columns such as attribute sample type, attribute replicates, injection order, if you have attribute batches. But it's important to provide attribute underscore prefix to that column so that GNPS recognizes that it contains this group information. Once, when you run this feature-based molecular networking with the metadata, GNPS also recognizes the group information, that it gets some intensity of these groups with which you can nicely play around within your molecular network. Am I clear? Okay. And then in addition to that, we also get these GNPS this annotation output tables, which is how this looks. You have this unique IDs, like from the Marcus session, and also Daniel have this feature ID, like the unique ID, the scan ID that you get from the mine as well as from the series. They all share the same ID with which you could combine them into kind of a master table so that you have all the information, feature, intensities, and then if they have some annotations, all those things in addition to the MZ retention time. Once you have all these tables, we could start basically with this pipeline. And until now, we've seen the first block in this preparation and pre-processing, how you collect your sample from LC-MS, yeah, you run the MZML files into MZMine and GNPS running molecular table, and you have this feature table. The protocol actually starts from the second block, which is the data pre-treatment. And here what we first do some cleanup, such as blank removal, imputation, normalization, scaling. This is also something that Josh nicely touched upon. And then we go into some multivariate statistics and invariant statistics. I'm not going to go deep into each of these sessions because it's already covered, but I just wanted to say a few things is that, like, yeah, batch correction is the for, and as mentioned here, it might be due to retention time shifts and the gradual contamination of the LC columns when you're measuring batches over a long period of time. And this is how PC post plot would look like if you look into the if you're looking for a batch effect as a simple process. First you run the PCA, and then you see if all of your QC samples, quality control samples, if they're all clustered, lying close together, it means that there is a less analytical variation. And if they are kind of far apart, it already shows that there is some variation among your full QCs that you need to correct for the batch effect. So, it is necessary to have QCs and also to have randomized samples. By randomized samples, I mean like to include blanks and QCs ones in between in the injection order. The next is the first important step also is to remove the blanks or like the blank features. So blanks are usually used to identify and correct for these contamination from the sample preparation. It could be different sorts of blanks, like solvent blanks, extraction blanks, so and so. For example, the methanol, which is what we use for resuspending the samples. So all of your samples also have these underlying. It's also necessary to remove all these background features from your feature table. This is what Stefan showed that you could also do that in mine. And yeah. So how do we do this feature, like this blank removal in FBMN stats? Is we define a cutoff between 0, 1, and we do this ratio-based removal of these blanks. So to simply put it, we calculate the average value of each features for in blanks and in also the samples. And then if the contribution is higher from the blanks, you basically kick out that entire feature. Based on the cutoff that you set between 0 to 1, which is between 0 to 100%, you determined as a user how much strict you want to be with your blank removal. For example, if 1, which is 100%, you basically want to retain all the features and you do not want to cut out anything. But then if you choose, for example, 0, you want to remove everything. And the recommended range that we use is between 0.1 and 0.3, which is between 10 and 30%. So this is how your feature table looks. And once you perform the blank removal, as you can see here, the blank samples and the respective corresponding features, which could have been part of all the other samples, is also removed. So you just have the different sort of samples. By samples, I mean like the control, treatment, all those things. And the second step is imputation. This is something we do also for PCA, because for PCA, it doesn't, correct me if I'm wrong, PCA doesn't allow with zeros like when we are doing with Euclidean distance. So we also do imputation. For imputation, we have these missing values in this feature table, which could be because of the molecule that we are trying to detect was below the analytical method's limit of. So the type of imputation we do is we pick the lowest value that is found in the table, and then we just generate random values, which is below the LOD, and we just randomly put it in the feature table. And as you can see, this is how the feature table, the dummy feature table looks like, and you have zeros here, and then we impute it with these lower number of random values, which you get down in LOD. For example, if your LOD is 400, you choose values which is below 400. Randomly put these values. And then there's either normalization or scaling. But I wanted to also show this nice example that we did this workshop where to show the difference between the different normalization or scaling techniques. So normalization basically reduces the variations across samples, and the one that we commonly use is TIC normalization or total ion current normalization. And yeah, people are now also increasingly using probabilistic quotient normalization. But the idea is that it normalizes based on your sample intensity. For example, in this case, they are trying to find a particular drug in which was given to all these like people, and they're trying to observe the drug in plasma as well as in the skin, which is basically two sample matrices, right? And when you see just after the blank removal, how it looks, the distribution of this particular drug that they were interested in, which is diphenhydramine. And in this, when you are looking at this plot in the x-axis, you see the intensity of the drug, and in the y-axis, sorry, in the y-axis, you see the intensity of the drug, and in x-axis, you see the time in minutes, which is 2 hours, 4 hours, 8 hours. Since it's given into through the bloodstream, you see in the beginning the plasma, which is in the red, that you observe it higher in the drug, so higher in the blood, and with time it decreases, and you also see that in the skin nicely increasing. But when you do TIC normalization, you can nicely see the difference between these two different sample matrices, which you did not observe in the normal case. And yeah, and also with the scaling, here we are adjusting the range of the peak abundances within each sample, and we're not doing it across the samples. And when you do scaling, you see that the values have been scaled if you look into the y-axis range. However, the information is contained, the matrix information are not taken into account. And we commonly use center scaling, which is like to contain all the main information around 0 instead of the mean of the metabolite concentrations. So these are the steps that we do in FBMN stats guide. And this is just as an information, because we are going to use the example that we used for all these days. Yeah, I think we can just, that's all I wanted to say, and we could just jump into the app. Yeah. I have already downloaded it. This is how it looks like when you open the zip file, FBMN Stats App 1.2. In case you don't have Windows OS, and if you're using other OS, you could use the web app, because this is .txt file, and I'm not sure how it would work for the other OS. Is everybody here? At least half of people are here. Then you can just go into the data preparation page. Here you can upload your data in different formats. You can manually upload your quantification table and metadata files. Else you could put in your GNPS task ID or GNPS2 task ID. It supports both of it. And there are a few example data sets that you can use to play around with, right? So for the purpose of this workshop, we would use GNPS2 task ID. And you can just go back to the resources page. Maybe you have the example FBMN job link, and then copy everything that is after task is equal to, which is the unique task ID. And I'm just going to copy the task ID here. And also there is this another line saying annotate metabolites. If you click this, it would replace your unique IDs with the annotation that was found. If you do not want to keep it, and if you do not want to add annotation, remove it by clicking on like this. I would keep it now for to include the annotation. So once we have all this, we can just go hit load files from GNPS. And then we have the quantification table and the metadata table that we uploaded for GNPS, the FBMN job. About what each of these question marks, which has this help information as well. And then you could also download these quantification table and metadata table. So now, if you look into the quantification table, the row names, which contains the concatenated form of some of the useful information from the feature table. The first is the scan ID or the feature ID, and the one that follows the underscore is your MZ value, and then the third part is the retention time. So since we clicked on annotate metabolites, one second. If you scroll through this, I hope to see, yeah, you can see that some of them are replaced with the annotations that were found, which is really intuitive when you're playing with some of the statistical analysis. And then you also have your metadata with different metadata categories. So some little information when you're making metadata is to just not change anything with the file name. For example, like whatever you got out of the MZMine feature table, copy that name and use it for your metadata creation, and to not change that. So once we have this, we can go for the data cleanup. You also have these nice little about sections, which have the figures to explain what these each of these steps do. As I said earlier, you take the samples and blanks separate, and you take their average value, and then you look into their ratio. And as I mentioned, you define a cutoff and you say, do I want to keep this or not? If you do not want to keep that, you just remove that entire feature. And this is for blank removal, and this is what we do for missing values. So I would come to this in a second. So now we can do blank removal. So everybody loaded in with their task ID. So we can click remove blank features. And then it shows the list of attributes that you have and the different levels of the different categories that you have in your attributes. And also the count information. For example, here we have 60 samples and 4 blanks. It's kind of swapped. But yeah. So once you have a preview of your metadata, you can go select it, attribute for sample selection. So which is the attribute column or the metadata column that contains the information about the samples and blanks. So this will be useful only if you have created or like added this information in your metadata, right? So it is also important to know that you put information in your metadata. So we have this information in attribute sample type, and yeah, it shows what are the different levels that you want to include. For example, if you added something like methanol blank, PPL blank, stuff like that, you could just add all those. Or if you added everything is just blank, as I did, you could just click in blank. And if you also click in, for example, sample, it would take in everything that is in there and would tell you you selected everything as sample type and it is not possible. So you just select the blanks and it already shows you what are the samples that you selected. And as you can see, we have the methanol blanks and the PPL blanks that are here. And similarly, we could also select, I made a mistake. I've selected blanks. I'm supposed to select samples because this is attribute for sample selection. And the blanks is down below. So it automatically selects the leftover, which is the blank. And then, yeah, there's this default value of 0.3. So it automatically calculates how much would go or considered as noise features. And it says like 28 features. I guess it was somewhere around 5,000 features when you get out of the MZ mine, and this is what will be removed. And once you remove it, you can see the number of features and the samples, because you'd be left with 4,000 some features and your 60 samples, which is the samples without blanks. And you could also play with the cutoff. Do I want to increase the cutoff? And then you can see the number of features are getting reduced, that you're letting more noise in. And you could also decrease it, the cutoff, and kick out more noise features. Are you following me? Okay. Yeah. And then we can, so now this step is done. We can go for imputation. And it also tells you the percentage of missing values in the data table. And then, as I mentioned, yeah. So it is actually down below the information about the imputation. This is the frequency plot, or like the histogram for the values like 0 to 1 and the values in 1 to 10, how many the number of values. Since we did imputation, you don't see any values in the zeros, but for example, if I don't press imputation, you see like the number of zeros in your data. And then you also have some of the information about like the number of missing values and the count, the histogram. So now I press imputation, tick the box, impute missing values, and then it gives you a preview or like a header of the imputed data. Nothing is changed with the number of features and samples. It's just the values are being replaced, the missing values. Can I continue? And for the data normalization, we have center scaling and then TIC, and you could also choose not to perform any normalization if you want. This session is also really useful for us to let everybody play with it, because there was a group who used it and they also came told us that there was a bug in the TIC, and it also helps us to improve it better. And yeah, we fixed it. So for this purpose, we would use center scaling. And then you submit data for statistics. It is not necessary that you do all these 3 steps to submit data for statistics. You could also not remove any blanks or anything like that and straight away submit the data for statistics. And and after each step, you could just submit it for the statistics, but I'm just doing all these 3 steps. Once you're done with that, this is what you get out of the data cleanup stage with your different attributes, like with one data table combined with the metadata and the feature table together. The first few columns are the metadata categories, and then starts the feature intensities for each of these features. You could also download this table. You could also download this table at this stage. And here, I just wanted to show that I've already downloaded a few things. Go back to the Eco-Metabolomics, FBMN stats. So here I already downloaded all those files. I just basically run it. After each step, I downloaded it, like right after blank removal, right after imputation. You cannot directly do it. You have to submit to statistics, and then you have to download the table. So for the purpose of I already downloaded it. This is something you could use for the next session with Daniel, incorporating this information into Cytoscape again to like bring everything nicely together. I also performed some ANOVA and random forest, which we can do now as well. So one more thing I wanted to, thing that I wanted to share is that, as you remember, I clicked annotate metabolites. So it already replaced the unique ID with all the metabolites names here, which would be difficult to get it back later. We would change that. But so in order to not disturb with removing this feature ID, I did not annotate metabolites in the folder, in the files that I generated. That is what you would find in the FBMN stats folder, so that you can also nicely separate these information and take these unique IDs and again go into Cytoscape, put it all together and the significant features, network visualization as well. So then, yeah, I'm just gonna show a simple PCA here just to see. And so if people are using multiple analysts, they could also tell me. So to my understanding, you cannot play around with multiple attributes at a time. So, but here you can play around with multiple attributes to see how it looks with different batches. This is all from just one batch. And if you look into the sample location, for example, there's a different 30 different locations. So, sample area. Thank you. So we have this huge variance, the PC1 with mission day, then the rest of the samples. So Daniel will talk about this in the next session, why you see this variance in the different regions. So you could then see what is in the different tabs with explain variances, describing you about how much percentage is of variance is explained by each PC. PC1 explains about 45% of variance, and PC2 explains about 6.93% of variance. And then you can also download the PC scores here. like if we want to go for a coffee break, we can also continue after that. Yeah, it's okay. We can finish it.